Ultra-reliable low-latency communications, or URLLC, is a new service in 5G New Radio and is becoming a critical component in next-G wireless communications. URLLC promises to offer 1 millisecond latency for communications between wireless air interfaces with a reliability exceeding 99.999%. It is designed to support delay-sensitive, mission-critical applications that require ultra-reliable delivery of data and minimum tolerance of latency. Example use cases of URLLC include industrial automation, robotic-assisted surgery, drone swarm, augmented reality for warfighters. For URLLC, reliability is defined as the block error rate, or BLER, which is a measure of the ratio of incorrectly received code blocks to the total number of transmitted code blocks. A target reliability of 99.9999% or 6 nines refers to the occurrence of 1 error per million transmitted code blocks. In a wireless environment, achieving this level of reliability would require some level of redundancy in transmission, both in space and spectrum. To achieve transmission redundancy in space, multiple transmitters are deployed in different locations to achieve diversity in space and joint transmission. In O-RAN, ORUs can be used for this purpose. To achieve transmission redundancy in spectrum, multiple resource blocks, or RBs, can be used jointly. When transmission redundancy in both space and spectrum is employed, how to optimally allocate wireless resources for URLLC becomes a critical problem. The goal is to deliver the required reliability for URLLC traffic. At the heart of the resource allocation problem is scheduling, which is how to assign the RBs at each ORU to different UEs in each scheduling time interval. In this demo, we consider a scheduling problem for URLLC in an industrial automation setting. We focus on downlink transmission from ORUs to the UEs. To maximize the reliability of URLLC data transmission to the UEs, we minimize the maximum BLER PK among all K UEs. As a first step, we need to quantify PK, or BLER mathematically. We employ the so-called Polyansky bound, which is a theoretical limit that builds on Shannon's capacity by focusing on small block sizes, just as one would encounter for URLLC. For each UEK, the Polyansky bound for BLER is calculated by applying the Q function to a fraction involving the SINR of each RB as well as the transmitted payload size. This RB allocation problem is NP-hard due to the non-convexity of the objective function and the calculation of SINR. Recall that our scheduling problem is to assign the RBs at each ORU to different UEs in each scheduling time interval. The solution space is k raised to the power of s times b, so an exhaustive search for an optimal solution is not feasible under our time constraint. Our proposed solution is called pistis, which is the personification of trust and reliability in Greek mythology. Pistis is the first scheduler under 5G O-RAN that aims to find a feasible solution to meet the 6-9 reliability requirement for URLLC traffic under 0.5 milliseconds. Pistis fully exploits the 3 control loops in O-RAN in its design. It consists of a non-real-time component, a near-real-time component, and a real-time component. In the non-real-time component, Pistis performs fine-tuning of several key parameters that will be used in the near-real-time component. In the near-real-time component, Pistis narrows down the search space by adding 3 sets of additional constraints. These constraints are derived from physical layer behaviors, such as O-RAN's joint transmission, channel slow fading characteristics, and reliability's dependency on the number of RBs. The outcome of the near real-time component is a set of feasible solutions that will be used as inputs to the real-time component. In Pistis real-time component, we compute the reliability of each solution. The reliability is calculated based on the Polyansky bound, which uses the real-time input of the channel's fast-fading behaviors. Then we compare the reliability for each solution and find the best one that offers the highest reliability. Now we elaborate on some key components in Pistis. The first component we want to highlight is how to narrow down the set of ORUs for joint transmission. In O-RAN, Joint transmission occurs when multiple ORUs simultaneously transmit identical data to the same UE on the same RB. Joint transmission can enhance the reliability of transmission by increasing the SINR. However, not every ORU is suitable for joint transmission. Only a subset of ORUs with good signal strengths should be considered. This motivates us to identify such a subset of ORUs on each RBB with respect to each UEK. The second component we want to highlight is how we guarantee transmission reliability. It is quite complex and time-consuming if we calculate reliability using the Polyansky bound directly. So we pursue a simple and fast approach to estimate reliability without too much compromise in accuracy. Pistis estimates reliability by counting the number of high-quality RBs allocated to a UE. To find out the high-quality RBs, we introduce a binary indicator delta. With the above selected RBs, we then estimate the reliability of a UE by counting how many RBs we actually need. Allocating more high-quality RBs means higher transmission reliability. To achieve 6-9 reliability, we set another predefined threshold, phi, representing the minimum required number of good RBs. Here, set S is the subset of eligible ORUs we found earlier. This constraint will ensure the number of high-quality RBs allocated to a UE meets the minimum required number. After reducing the search space, there remains a pool of feasible solutions. Pistis now computes the Polyansky bound for each solution in parallel using fast-fading channel information. Then it chooses the feasible solution that offers the lowest BLER. This entire calculation process takes place in the NVIDIA GPU, and it is in the ORAN real-time control loop. To demonstrate Pistis performance, we simulate a drone park with 4 ORUs and 40 UEs in a 100 meters x 100 meters area. The 4 ORUs are located as shown. Each of the 40 UEs represents a drone flying randomly in the park at low speed. We use 40 RBs at each ORU. This figure demonstrates Pistis running time, which shows that the running time is always below the 0.5 milliseconds timing requirement. For comparison, this figure shows the running times of the max-min resource scheduling algorithm. The average running time for MR is 24.2 milliseconds for 1 mini-slot, which is nearly 50 times of the 0.5 milliseconds timing requirements. Regarding reliability, the highest BLER Pistis experienced is 2 times 10 to the negative 35. This is much lower than the 10 to the negative 6 URLLC requirement. In contrast, the average BLER experienced by the MR scheduling algorithm is 0.732, which is more than 5 orders of magnitude higher than the BLER requirement. This concludes our demonstration of Pistis, a real-time scheduler adeptly designed for the stringent reliability and latency requirements of URLLC. Thank you for watching.